Okay, let's start. In today's lecture, we are going to learn some advanced algorithms in testing. So here is today's outline. So we will try to model the testing process as a search or optimization problem, and then apply some searching or optimization algorithms to help testing. And then we can also learn about how can we model some decisions in or some designs in testing as multi-armed bandit problem, and then apply some corresponding algorithms to solve the problem. So before we start to learn the new knowledge, let's revisit what we have learned. So we have learned how do we create test cases, right? So fundamentally for software testing, it is it's just to try to run the target program with some kind of input and then observe for what happens. So, but we are not trying any input. We are not trying all the inputs randomly because the search space, the input space is very large. We have to have some well-designed inputs to trigger some special behaviors of the program, right? So instead of trying all the any arbitrary input, we create test cases to find faults, to obtain some coverage or some over some structural elements like statements, branches, right? So, and we can also try to design test cases to cover some combinations of some representative values, like doing some boundary value testing or some equivalence class testing. So, and maybe we can also try to create test cases to execute some def-use pairs if we care about the control flow, etc. So we have some purpose when we create these test cases. And the test cases that can fulfill this, the test cases can fulfill the targets are the desired test cases we want, right? So what does these targets all have in common is that we have some objective to achieve with the set of test cases we are creating. So that's why we can model testing as a search problem. So we have a goal to achieve when we do testing, when we design the test cases. And this goal can actually be measured, right? Because for most of the time, we can measure the coverage, we can measure the code pairs, we can measure the def-use pairs as well. So in this sense, we are kind of searching for a desired test suite that can fulfill the goal. So this is why we can think of testing as a searching problem. So we are searching for a suitable set of test cases. So in this case, we are trying to, from the nearly infinite input space, we are trying to search for a subset that can fulfill our targets. And these targets could be obeying certain properties, or for example, we can try to find some boundary values, right? These are some properties. And we can also try to find the test inputs that can cover all the statements, branches, or paths, right? And this is related to white box testing. And we can also try to find the test cases that can cover all the two-way pairs of representative values, right? And these two-way pairs is actually related to combinatorial testing, right? So we can actually try to find a set of inputs that is desired, that can fulfill some objectives here. So we are kind of like searching for such a set from an infinite space, search space. So this is why testing could be viewed as a searching problem. And we have learned that, but for this, we just answered the first question. We can achieve some goals, but we need these goals to be measurable, right? And we have learned that it is actually the most desirable test suite is the test suite that can help us to find all the bugs in the software. But it is like impossible to find all the faults inside a piece of software, right? So this is not a good measurement. But the testing goals can be measured. Like, for example, whether a property has been satisfied or not. The property could be like the value of the test case taking some boundary values, right? It's either true or false, right? So this is measurable. And some of the goals are numeric. For example, we can check the percentage of coverage we can achieve with the set of test cases. So these testing goals, these Boolean or numeric test goals could be measured. And if we can measure them, then we can actually use computers we can write programs to automatically do the searching for us. So this is why we can automate this searching process using some algorithms here. And there are actually many search techniques for automated test case generation. So this is why, because these testing goals are measurable, then we can try to automate them with programs. And a typical searching process is like this. So we choose a solution from the solution space and check whether this solution can help us to achieve the goal. And if this solution cannot be used to achieve the goal, then we try another one, right? So this is like a typical searching process. And we should keep trying new solutions until the goal is achieved, or we have tried out all the possible solutions, right? And in this sense, the order of the solutions, of trying out different solutions, is important for finding the final solution, like the most suitable solution efficiently, right? Because if we put the optimal solution like earlier in the queue of trying, then it's more likely that we are finding that solution earlier, right? And a search, therefore we should have some strategies when we do the search, when we try to arrange the direction of doing the search. So we need to have some strategies here. And these strategies are also known as heuristics here. So heuristics are used to choose the solutions to try out and ignore the unviable solutions, right? The infeasible ones. And talking about efficiency, let's think about this problem. Actually, when we learn gray box fuzzing, we know that these gray box fuzzers actually maintains a pool or a queue of seeds to try out. And we just learned that the order of how we organize the solutions is important for like improving the efficiency of finding the suitable solution here. So So seed prioritization is actually reordering the seeds, right? It actually helps us to determine which seed to use next. And each seed is actually like a solution here, right? So it's actually affecting the efficiency here. So do you think seed prioritization strategy can affect the code coverage after the fuzzing process converges? Like, for example, this is actually a figure from a report of a fuzzing campaign. So the y-axis is the number of edges covered, and the x-axis is the time used. So we can see that the fuzzing process can converge after a certain time, right? The coverage stops growing after some time of fuzzing. So do you think seed prioritization can affect like the final coverage here after convergence or not? Let's see the results. Yes. Actually, the correct answer is no. So let's see why. Because we can see the order of solutions that the order of trying out the solution affects efficiency here. And we have learned the difference between efficiency and effectiveness, right? Efficiency actually, so let's continue. So efficiency actually is related to the speed of reaching convergence. So, by reordering the seed, by putting the better seed as earlier in some earlier positions of the queue, we can actually increase the code coverage faster. But because it only affects the order of the solution, we are still trying out all the solutions, right? We are still trying out all the seeds, no matter how it is ordered. So it doesn't affect the final coverage achieved as far as we eventually try out all the seeds given enough time. So that's why the ordering of the solutions here only affects how fast we can find the optimal solution, but it doesn't affect like how good is the best solution here. So actually efficiency is kind of like related to how fast we can converge, and effectiveness is actually related to the final coverage after convergence. So if we only reorder the solutions, the order of trying out the solutions, then it can only help us to achieve, to get the better results faster, but it doesn't affect the quality of the best solution. So this is the characteristic of like improving efficiency. And that's just an example of doing searching in fuzzing. And a more common scenario of doing search is like we are doing some search in some trees or some graphs, right? So when we search, maybe I think you have learned some algorithms like courses in year 2. So when we do a search in like a graph, we can actually use some heuristics there. And if we don't use any like heuristic, what we normally do is like we can do a BFS, right? We can do a breadth first search. We can try out the nodes layer by layer on the graph. And we can also do a DFS, which means that we try to reach the bottommost node first, and then we do some recursion to get back and try out and gradually visit all the nodes in the graph. So this is like, these are the two most common heuristics we do when we try to do a search on graph. And they are like easy to implement and understand, right? BFS and DFS. And we can also have some more advanced heuristics here when we do a search on a graph. For example, we can do the A-star search. So what we do is, whenever we are at a certain node, we try to estimate the shortest path towards a target node. Then we just choose that, and this estimation of the shortest path could be time or distance. And then we examine all the possible next moves, and we try to just choose the one with the shortest, like the least effort for reaching the goal. So this is like the A-star search. And you can see that this actually requires the estimation of the distance or time is important here. And it's kind of like related to some domain-specific knowledge, right? We have to like choose the estimation according to the actual problem we are facing. And we can see here that because we are trying to estimate something, this heuristic is like more complicated, and it is actually like, because we are like estimating something, we are like assuming that like something is going to happen. So it is this is why it's called a heuristic here. So this is like some examples of heuristics when we do search on graphs. So this is because we are applying some more complex heuristics here, then it's considered to be a smart searching algorithm. And talking about searching for software testing, and actually there is like a term called search-based software testing. And now this term has become like, it is actually used by a workshop plus a competition event in some academic conferences. And now this term has been changed from search-based software testing to search-based, can you guess what is the F here? Is search-based fuzz testing. So you can see this. So this is the last year's event, which is search-based and fuzz testing. So this actually shows the popularity of fuzzing here. So that's why we are learning fuzzing in this course. But unfortunately, they are not holding. They have some fuzzing competitions in last year, but in this year they have canceled the fuzzing competition due to some technical constraints. And talking about doing search, we always have some search budgets, because just now we learned that when shall we stop searching, right? When we have found the solution we want, or we have tried out all the possible solutions, right? But when in testing, it is impossible to try out all the possible solutions, right? Because the input space is kind of like infinite. We cannot try out all the possible inputs for a program. So we have to have some budget when we do this searching here. And of course, the ideal case is that all solutions should be tried, but actually, because we don't have enough time and money to try out all the solutions, and because it's kind of like infinite, so we cannot try out all the solutions. So we have to somehow add some constraints to the problem. And that's why we need to introduce a search budget. And this budget could be in the form of limiting the number of attempts we try. And we can also try to limit according to the time allocated to do the search. And because we are constraining the problem with a budget, it's kind of like we try to find a solution before the budget expires. So that's why we are kind of like moving from simply searching to optimizing, because sometimes we cannot find a desirable solution before we run out of budget. So in that case, do we say that, okay, we have failed the searching process? Then that's not the ideal case, right? So it is actually, sometimes it's very hard to solve some problems or achieve some goals under a budget. And if we cannot achieve that goal, we don't just simply say that we failed the process. Instead, what we want is we can try to because if we just use some binary goals like pass or fail or true or false, then if we cannot find a satisfying solution, then the result is kind of unknown, right? That's not what we want. So what we want is like this. We want to, instead of trying to find the solution that can satisfy some goals, what we want is we can somehow transform this finding of the best solution into a problem of optimization. What it means is that we can, instead of trying to find the best test suite, what we want is we can try to optimize the set of test cases. We can try to find the best possible test cases that we can find within the budget. So instead of finding the best solution, we can find the best possible solution. And this actually requires us to optimize the test cases, right? We are trying to improve the overall quality of all the test cases here. And in this sense, we are allowing, because we know that the optimal solution may not be the best solution. So that's why it is also, it is called partial solutions here. So instead of just succeed or fail, what we want is we want the optimal solution to be found. So that's why we can actually also convert the testing problem into an optimization problem. So in this case, we are searching for the best possible solution given within the budget. And this somehow is kind of similar to local or global optimal. So a search problem is to find the global optimal, but if we cannot find the global optimal within the budget, within before running out of the budget, we can just find the best solution we can have locally here, right? So this is somehow similar to this. And now let's try to formulate testing as an optimization problem formally here. So we know that instead of finding the best solution, we can find the best possible solution. And therefore, the heuristic becomes important here, right? Because we are trying to, because we have a limited budget, we cannot exhaustively try out everything. So we have to maximize the output of the outcome we can get within the budget. So if it is time bounded, then the time to create or execute and evaluate the solution is important, right? And if it's bounded by attempts, then the strategy used to choose the solution is important, right? And for the assignment 3, do you think the question 5 is time bounded or attempt bounded? Yes, it's actually attempt bounded. So the strategy to choose which seed is good, or the strategy to generate new test case is more important, right? So we don't care about time. So you can try to create some very complex seed inputs or test cases. That takes some time, but it doesn't matter. We just care about the strategy for choosing these test cases. And but that's for the assignment. And in practice, actually, we want both. So we want both the time to be fast enough, and we also want the strategy to be smart enough. And there are actually many search strategies that we can use to do these optimization problems. And we are going to learn one of them, which is known as genetic algorithm. And let's continue to explain more like why this genetic algorithm is suitable for solving this optimization problem. So normally the optimization problem is to find the best solution under some constraints. And sometimes it's like, because there are so many restrictions, it is like feasible for us to exhaustively try out the search. So that's the case here. And because we cannot try out all the inputs for the complex systems, right? So we need a strategy to sample some good inputs from the entire input space, but we don't really want to like do it randomly. So the question becomes, how can we find this best possible solution given this limited budget, right? So we can apply these optimization problems. And the set of optimization problem that is suitable for this is called meta-heuristic search techniques. And meta-heuristic, just now we learned we have some heuristic approaches, right? Because heuristic is like A* searching is a typical heuristic based. And A* requires us to be able to estimate the cost, right? To estimate the shortest path. But here, the problem is that sometimes it's impractical to do this estimation. And we don't have the domain knowledge, like some domain-specific knowledge to do this estimation. We need to find a more generic algorithm. And this set of algorithm is known as meta-heuristic algorithm. So you can click on this link to get to the wiki page, which has a large portion of boring definition of meta-heuristic. But based on my understanding, the difference between heuristic and meta-heuristic is that meta-heuristic doesn't require us to know exactly how good a solution is. Meta-heuristic just allow us to know that, okay, we are moving towards the correct direction, but we don't know like how good we are. So that is meta-heuristic. So meta-heuristic is like, we don't need to know exactly how good we are. That's heuristic. Meta-heuristic is like, we just need to know we are moving in the correct direction. We are getting better, but we don't know how good we are. So this is meta-heuristic. So that's why, because we know that we are getting better, it means that we don't need that many specific domain knowledge, right? And this is like an analog for like meta-heuristic. So meta-heuristic is also known as the heuristics to generate more heuristics. So if we use it like and to compare with like the usage of some values, some random value is like this. So the most naive way of using some seed value is to use a fixed seed value for doing something. And a better solution is like we can use a random number with a known seed and add some parameters. And then we can also try to like improve it by using the system time as the seed, right? And then we can also try to use a random number generator to generate the seed for using the random number generator to generate another number. And this is like meta-heuristic. So generating a random seed, generating a random number is like the heuristic. And using the random number to generate, to add the seed to generate another random number, then this is meta-heuristic. So it's a heuristic of heuristics. And because let's further like define this problem better. So because we can try to calculate like the if we can like because like we know that we are not searching for the best solution. We just try to search for a better solution. And in order to define better, we need to have some scores, right? And then if we can have this kind of score, we are getting closer. This score is becoming our optimization target. So now we have enough like concepts to define this better. So if we revise the definition of test generation as an optimization problem, it could be like this. So what we can do is we can generate a test or a set of test cases, and then we can score them using something called a fitness function here. And this fitness function is actually calculating the score as the optimization target. So this is how it works. And then we can try to manipulate the solution or the solutions we have according to some search strategies. And this manipulation here is like the meta-heuristic. So this actually gives us the body of the genetic algorithm. So we know that we have a target, we have a scoring system to know that we are getting better, whether we are getting better or not. And then we also need to like use some meta-heuristics to create different variations to be scored, right? So this is roughly how it works. And talking about genetic algorithm, it's a special type of meta-heuristic algorithms. And it's actually inspired by some as you can see from the name, it's actually inspired by some biology concepts. And the key idea is over multiple generations of the population, let's try to evolve the population to make the whole population better by favoring good solutions, like favoring good individuals in the population and filter out bad ones. So this is like how the things are like the creators are evolving in the context of biology, right? So that's why it's called genetic algorithm. And because we need to find a better solution, like we need to try out different solutions inside the search space. We need to make the whole population diverse. And this diversity is introduced into the population in each generation by keeping some of the both best solutions. This actually, the keeping of the best solution is to make sure that we are moving towards the goal. We are trying to get things better. And we randomly generate some new members into the population. And then we can create offsprings by mutations and crossover of the genes. So this is like a rough idea of like how genetic works. So it's basically combining some good features of the parents to create some new members into the population. And there are some key concepts. We just covered actually some keywords in this algorithm, but now let's introduce the key concepts of this algorithm in detail. So we know that this is actually the chromosome and gene. I believe you might have learned about this in biology. And chromosomes are actually the units that carries the genetic information, and genes are like the actual items on the actual information of the chromosomes, right? So individuals on the population, so each chromosome is considered as an individual inside the population, and each gene is considered to be as some characteristics or properties of the individual. So individual and population compete for resources and reproduce. And the individuals which are successful according to the fitness function are allowed to be kept in the population to reproduce and create more offspring than others. And then, therefore, the genes from the fittest parents propagate through can be kept across different generations. And that is like why sometimes the offspring is better than both parents, right? And therefore, because we are keeping better things and we are like getting rid of the worst genes, then it is like we are moving the whole population towards a better, a more desired like solution. And this more suited for the environment is actually defined by the definition of fitness function. And actually the chromosomes, actually they are corresponding to the individuals, and the genes are actually the properties of different individuals. So actually, if you look at this slide, and if someone just come in right now, they may think that, okay, this is not a computer science course, maybe this is a biology course, but actually this is like what we can learn from like biology. So we can try to convert this into some algorithms. And of course, the population is actually the set of the individuals, right? The set of the chromosomes. So this is a typical workflow of the genetic algorithm. So what we do is, first, we initialize the population with a set of random inputs, a set of random like individuals inside this initial site. And then we can reproduce, because the initial site is only a small space inside the big search space, right? It's only a small part of the big search space. We need to somehow generate new individuals to explore the search space, right? So the process of generating the new inputs, the new individuals is known as reproducing. And we need to make sure that the entire population move towards certain goal, right? Move towards certain target. And in order to move the entire population towards that target, we need to actually eliminate some of the bad individuals in the population. And this is actually done by using the fitness function here. And then we have to make sure that we can finish this entire process, right? This entire process should converge, right? Normally it's limited by the number of generations. Let's say that we do maybe like 100 generations, then we stop. Then that the final generation we have, the final generation of the population we have is considered as of our optimal solution here. So this is like genetic algorithm. So we are doing this loop of like, once we have the initial population, we just reproduce to generate new individuals to put new individuals into the population, and then eliminate the worst ones, and then generate again and again until we run out of the budget. So this is how it works. And genetic algorithm is like used in many different scenarios of testing. And for unit testing, actually there is a very famous tool called EvoSuite, and this is a website of the tool, and it is actually created by some people in Germany, and it's an automated test suite generator for Java. So you can, if you're interested, you can click on this link and try it out. And you can see that the main feature is actually to use genetic algorithms to optimize towards certain targets. And these targets you can see here could be the coverage criteria, right? And this tool was actually created in 2010. And this is like considered as a new technique or young technique in comparing with all the, very classic algorithms we are learning here. So it's a new technique. And actually, American Fuzzy Lab, like what we have learned in the last week, is also somehow using this genetic algorithm. You can have a feeling about it, right? Because, but there are some differences. So the initial seeds, so the pool of the seed inputs, the test inputs, is like the population, right? We are actually moving the population towards like a population that can have better edge or branch coverage. So the initialization is like, instead of like randomly generating some seeds, we can like ask the user to provide some initial seeds. And there are some differences here. So instead of like always combining the parents together to create the offspring, we can mutate a single parent, right? And this is actually what we are doing for assignment 3. We do one of the to-dos is to implement the mutation function, right? So we can create new individuals into the population by mutating a single parent. And for the survival here, AFL doesn't kill any individuals. So we don't drop any seed from the population. So we are actually keeping all the seeds. So this is actually also similar to what you are trying to do in assignment 3. You need to figure out how should we keep new seeds and under what criteria. And for termination, instead of like using the number of generations, normally for AFL, we just use time for stopping. But for this assignment, we just use the number of attempts. And here is an example of using genetic algorithm to guess a random string. So we can click on here. So we can consider this as like this. So each individual in the population is like a string, and each gene is a character. And for AFL, can you like imagine what is like each chromosome? Like each test input is a chromosome. And what is a gene? The gene in this AFL example is actually the byte of the actual content of the test input, right, of the seed. So we can try out this genetic algorithm. You can see that we are actually starting from like a random population. So this population is like initially we have like 1,000 population, and then the initial population is made up of several like random strings, 100 random strings, and our goal here is to actually evolve this entire population to eventually make sure that one of the individual string inside this population can meet can take the value of our target string. So this is how it works, and we can run it. You can see initially we are like the fitness function here could be defined as like how many characters matches our target string, right? And you can see initially the best solution is something like this, and throughout across the generations, we can see that the best solution is kind of like getting better and better from the output log, right? You can see here. So we are actually gradually getting the optimal solution better and better. And you can feel free to make adjustments to make sure that to try out this example here. For example, you can try to make the target string longer, right? Maybe let's try hello world comp 3142. Then if we run this program, do you expect the generation to find the target string to be longer or not? Should be longer, right? So you can see maybe we are not able to find this within the 1,000 generation. So you can see that we didn't even find the result within this time budget, within the budget. But we know that we are like getting better and better, right? The solution here. So if we make this, there are some randomness in this algorithm because we are actually generating the offstring with some random mutations, right? So if we run this multiple different times, we can get different results. Like how long does it take for us to find the suitable solution, or whether we can find the optimal solution within the budget or not. So you can see that this time we run this algorithm again, and we can find the target string within the budget we have. So that's an example of using the genetic algorithm to guess a string. And a string is just like a special case of any random bytes of inputs, right? So you can imagine that we can also try to use this genetic algorithm to find the best test inputs. And that's all for the first half of today's lecture. And let's take a 10 minutes break. And I'll see you at 3 after 5. Today or tomorrow. Yeah. Okay, let's start. So the second half is that it's kind of like similar to the first half. We can somehow model the testing process as some typical or classical problem, and then we can apply some algorithms which are derived from that problem to help the testing process. So this is what we can do. And the problem we are trying to learn here is called multi-armed bandit problem. And the keyword here is the bandit machine. And it actually looks, looks like this. So you can see this. There's a painting of a bandit on this machine, and you just pull this arm, and you have a chance to win the award. So win some award, but you need to put in some coins first. So do you know why this is like called a bandit machine? Because it's kind of like it's gambling, right? It's gambling because you will surrender your money to it. So it's like robbing money from you. So that's why it's called bandit machine. So don't gamble. But there are some good algorithms from the gamblers, because the gamblers are, if you are master gambler, then you must be a very good mathematician, who is good at like the probabilistics. So there are some good algorithms from the gamblers. For example, the Monte Carlo simulation, and this is actually one of the key algorithms used in AlphaGo. And if you wonder what is Monte Carlo, it's actually a name of a famous casino. So this is actually based on some gambling strategies. And this is like a bandit machine. So we know that, okay, if we pull the arm, but we need to pay some tokens, right? We need to pay the token first, and then we pull the arm. And then we can have a chance to get some reward. And the multi-arm bandit problem is like this. So there are several arms. So it is kind of like a machine with multiple arms. And each arm is actually associated with a different probabilistic of getting us some reward. So, and it's considered like a machine with multiple arms, or multiple one-armed machines like this. So each one of them is actually associated with a fixed probability of getting us some reward. You can see here, this machine actually has the highest probability of getting us a reward. And if we know this probability, then we should always play this machine, right? And we should avoid the machines with like lower probabilities of getting us a reward. So, but the key is we don't know the probability of getting a reward for each machine here beforehand. So we don't know this. So here in this setting, in this problem, each machine actually, we consider them to have a fixed chance of randomly giving out an award. So once the chance is initialized, then it never changes. And the constraint here is that we can only pull the arm for fixed times of n here. So this is our budget. So we cannot like pull the arm for infinite number of times because we have limited number of tokens, right? So let's assume that we can, if we have 100 tokens, then we can pull the arms 100 times. And how can we maximize the reward we can get, right? Then this is a problem. So if we can only pull the arms with a limited number of time, how can we get the highest reward is the multi-arm bandit problem. So this is a problem. And the key concept, the key strategy here is to balance between explore and exploit. And before we introduce the actual concept of explore and exploit, let's try to have a guess. So if we always pull the machine, if we know that, okay, this machine has the highest chance of giving us a reward, and we always pull the arm of this machine here, then is this behavior considered as a behavior of exploring or a behavior of exploiting? What do you think? So if we always choose the machine with the highest chance, then are we doing exploration or are we doing exploitation? Let's see the result. Exploit, yes, because we are kind of like leveraging the knowledge we have, right? We are making use of the knowledge that this machine has the highest chance. So that is exploit. So explore is like we are trying out different arms to collect more information about their reward distribution, because in reality we don't know the chances beforehand. We don't know what is the chance of getting a reward from each machine. So we need to do explore, and exploit is that with the current knowledge of the distribution or the chance of getting a reward for each machine, we try to choose the arm that can give us the highest reward. So we need, as you can imagine, because we have limited number of chances of trying, we need to balance between explore and exploit, right? If we don't do exploration, we don't know which machine is going to give us a higher chance of getting the reward. And if we don't do exploitation, we are not like getting the best rewards, right? If we know that, okay, a machine has a higher chance of getting us a reward, and we don't choose that machine, then we are wasting our chances to get reward, right? So if we do too much of exploration, then we are wasting our knowledge, right? We are wasting time on the arms that has lower chances. And if we do too much of exploitation without doing enough exploration, we might be pulling the wrong arm, right? Because of the randomness, maybe we are not estimating which machine is good enough, right? When we don't have enough like knowledge of which machine is the best. So we should do a trade-off between explore and exploit. And if we think about this problem in gray box fuzzing, it is kind of like this. So let's assume that achieving coverage is the reward. So if we can achieve more branch or edge coverage, then we are getting more reward. And each seed could be considered as a machine or an arm to pull. So because we can select, we have a pool of seeds, we can select which seed to use to generate new test cases, right? We need to find the best test case that is more likely to give us a higher chance of like better coverage, right? So each seed here could be considered as a machine. And each mutation operator could also be considered as a machine, because like in the assignment 3, you are implementing two different types of mutation operators, right? Using the interesting values or doing some like byte level random mutations. So we have many, many different mutation operators, but which one should we apply here is like the question here, the decision we need to make, right? And the process of choosing which mutation operator to apply is somehow similar, like choosing which arm to pull, right? So we can also consider this as machine or an arm. So that's why. And what about the limit here? The tokens we have, the budget, we can actually use like the number of executions as the tokens we put into the machine, or the effort we are devoting to this system. So what we can do is like this. For every X executions, we can use a portion of the executions to explore and use the rest of the executions to exploit. And it's kind of similar to using attempts and time as the budget in the optimization problem. We can also try to use a slice of time as the number, like as the token we are using here. So we can actually divide the entire like time budget into several different time slots, and for every like X time slots, we can use a portion of the time slots to explore and the rest of them to do exploit. So this is how we can convert like the fuzzing decisions as into like multi-arm bandit problem. And but this is like a very subtle point. So sometimes we know that, okay, this is a very good analog. We can try to model gray box fuzzing as a multi-arm bandit machine problem. But based on my experience, actually this is not a good modeling here, because remember the assumption for multi-arm bandit problem is that each machine here has a fixed chance of giving us a reward. So this assumption means that this chance of getting a reward never changes as we pull the arm. But in fuzzing, actually the chance of getting the reward dynamically changes in fuzzing, because you can imagine that if we consider each seed as a machine, the more we use a particular seed, the lower the chance it will give us more coverage, right? Because we have already tried out the different test cases with that seed. If our target is to find new coverage, the more we use a particular seed, the lower the chance we are getting some new coverage. So based on my personal experience, this modeling of gray box fuzzing as a multi-arm bandit problem is like an oversimplification. So but that's very but in this course we can just think of gray box fuzzing as this problem here as a simplification. So in this course, let's just keep things simple. And that's how we can model testing as multi-arm bandit problem. And now let's think of some algorithms to solve this problem here. And the algorithm we are going to learn is actually the most simple algorithm for solving this problem, which is known as epsilon greedy algorithm. So the epsilon greedy algorithm actually allows the agent to decide whether to explore or exploit at each step. So every time it spends a token, it can make the decision of whether this token should be used for exploration or exploitation. And it is done like this. So with a probabilistic epsilon, with the value of epsilon, the agent will just explore a random arm or a random machine. And with the probabilistic of 1 minus epsilon, the agent will just exploit based on what it has observed. So the exploit is defined by this. So it will just use the token to pull the arm that has given us the highest reward for now. So this is the action of exploitation. So it is very simple, right? You can see that we just use a small we just use like a fixed epsilon value here to determine, like, it's like flipping a coin. So we are just using this epsilon value here to determine whether we do exploration or exploitation. And however, there is a key here. So do you know why this value is called epsilon here, but not any like other Greek alphabet? The reason is that it's based on my guessing. So I don't know if this is really why it's called epsilon, but epsilon often refers to a small number. So if we have a small number, we use epsilon to denote that number. So in this algorithm here, this probabilistic epsilon should be a small number. And we will learn about why later. So that's the key idea of epsilon greedy, and let's try to formalize the process. So what we do is we first do initialization. So because initially we have no idea of like the chances of each machine or each arm, right? We have to assign some estimated like value for each machine. And normally we just set the initial values to 0, like none of them is like going to give us any reward. And then we also need to define an epsilon value here to determine the chances for doing exploitation and exploration. So this value is normally very small. We can use like something like 0.1 or 0.01. And then the next step is after we have done the initialization, we can do the action selection according to the epsilon value, right? So we just create a random number and compare it with epsilon value. If the value is smaller than epsilon, then we just randomly select an action to do, randomly select an arm. And if the value is like larger than epsilon and smaller than 1, then we just select the action with the highest current estimated award. And after we pull the arm, we just collect the reward, right? And because this reward collection is needed for us to build the knowledge about each machine, right? So this is reward collection. And then after collecting the reward, we also need to update the estimation. We need to check which machine is giving us a better chance of like getting a better result. So this is how it works. And then we repeat until we find a suitable solution, or we run out of tokens. So this is how it is done. And there are several pros and cons for epsilon greedy. So the pros are very obvious. So it's very simple and easy to implement, as we can see. And it's actually a straightforward approach for balancing exploration and exploitation. And but this is like somehow like both a pro and a con. So we can adaptively adjust the value of epsilon according to different problem settings. So, but we have to do it manually, right? So the con is that the first one is coming from this. So this is not very adaptive, because we need to manually specify this value of epsilon before we start trying out the entire process of solving the problem. But we don't change it during the the entire process, right? So it's a static value, and maybe the value is not suitable, but we have to bear with it and run it all the way. And there are actually some like more advanced strategies, like the upper confidence bound or some Thompson sampling, which can really mitigate the problem of using a fixed epsilon assumption here. But they may potentially outperform epsilon greedy, but they are like, if you're interested, you can click on the link to check them out, but we are just going to learn epsilon greedy here in this course. And let's try to see an example of how can we use this epsilon greedy to play this game here. So let's assume the setup of the game is like this. So we have 5 arms, and each arm is equipped with a chance of getting us a reward randomly. So and the chance is always between 0 and 1, right? Is each machine, or each arm here, has a chance to give us a reward. And this reward and this chance is like just a random number between 0 and 1. And then we can have, like, let's say we run this for 1,000 times. So we have 1,000 chances to try out each machine or each arm here. And we can try to use our strategy to get the best reward. And let's assume that we use the epsilon value of 0.1, and we can run the program. You can make some observations here. You can see that for this run, the best arm has a chance of 0.86 for getting us a reward. You can see these are the chances for each arm to give us a reward. You can see 0.86 is the largest value here, right? So if we know this probabilistic here, then we just always use this arm, right? But we don't know it beforehand. It's a black box for us. So the epsilon greedy reward here on average can give us like 800 and something over 1,000 pools. And if we do it randomly, it's like 500 something. And you can run it multiple times. You can see that this time the best arm is like 0.67, and the epsilon greedy can give us like 600 something, and random is like 300 something. You can see this time is 0.92, and epsilon greedy is 800 something, and random is 500 something. So the random strategy should always like give us a reward which is around 500. So do you know why it's like always 500? Because it's 1,000 times 0.5, right? Because each arm here is equipped with a random chance. Each arm here is initialized with a random chance of giving us a reward. And this random number is like, because it's sampled from 0 to 1, so it's always like the estimated value is, or the expected value is 0.5, right? So it's 1,000 times 0.5, which is 500. So this random strategy should always give us like a value similar, like around 500 or close to 500. And epsilon greedy should give us like roughly, but always, like almost always smaller than the best machine probability times 1,000, right? As we can observe. The reason is kind of obvious, because we are having like, because we because we are using a larger chance to do exploitation. So once we accumulate our knowledge to figure out which machine or which arm is the best, we will have a very big chance, like 1 minus epsilon, to use that machine, right? So it's near optimal. So that's why the epsilon greedy should give us like something like smaller than the best machine probability times 1,000. And you can also try to play around this by modifying the values here. So if I modify, let's say if I change the value from 0.1 to 0.5, what do you think is the value here again? Do you think it will get better or worse? The epsilon greedy reward if I change the epsilon value to 0.5. So it's like we are using half of our chances to do exploration and half of the chances, the tokens to do exploitation. Do you think it's getting higher or lower? It's actually lower. You can see the estimated value is 0.56, so it should be close to 560 something, right? But it's like only 400. You see this is quite obvious, right? Because we are doing too much exploration this time. We don't have enough, we are wasting our tokens on some non-optimal arms. So this is epsilon equals to 0.5. And what if we change the epsilon value to 1? It's kind of like random, right? It's essentially random, right? It's all exploration, no exploitation, right? We can see the result is just like random. It's very similar to random. If we do this, it's kind of similar to random. And what if we change the value to 0.001? Will we get good result or not? 0.001 means that we are using like an estimated value of like 10 tokens out of 1,000 to do exploration. And we have 5 machines. We use 10 tokens to explore which one is the best. So in this case, it's worse, right? It's generally worse because it's kind of similar to random, because if the value of epsilon is small enough, like if we do this, like if we add 1 more 0, which means that we are only using 1 token to explore which machine is the best out of the 5, then it's essentially the same as random again. So almost the same as random. But this is like because of the random number generator. It's like sometimes we may get lucky to get some better results, but it's essentially almost random here if we make the value too small, because we simply don't have enough exploration to decide which machine is the best. And if we don't decide which machine is the best, then it's likely that we are getting a worse result. And if we change this number of arms to 10, it will be more obvious. You see here. I don't know why this in this in this example is not it's so good, but let's run a few more times. 0.06, 0.38. It's always similar to this value here. Let's add one more 0 here. It should be similar to random, but it's always similar to the estimated value here. Maybe there are some issue with the random generator, number generator setup, but the key idea is that if the epsilon value is too small, if this value is too small, then we are like essentially still doing random strategy. And if this value is too large, like 1, we are still doing like random exploration. So it shouldn't be too large or too small. And 0.1 is like normally a good value for epsilon greedy. So this is the example program. You can try to play with it and try to adjust like different settings. Like for example, if you can increase the number of arms, what will happen, right? If you increase the number of trails, what will happen? So you can try this out on your own. You can feel free to modify this program. And that's all for today's lecture. And before we end today's lecture, let's have a quick recap of what we have learned. So today we have learned some advanced algorithms for doing testing. And these algorithms are they are not coming out of nowhere. They are actually associated to how we model the problem, the testing as certain problem. So we can model testing as a search problem. We can model a testing as an optimization problem. So if we model testing as a search problem, then we are kind of like searching for a suitable or desired set of test cases. And if we view testing as an optimization problem, then what we do is we are searching for the best possible set of test cases within the search budget. And in other words, it's kind of like we are optimizing the entire set of test cases towards some desired goal, right? And in order to do this, we can use the genetic algorithm by trying to increase the diversity of the population by doing some mutations or generating some offsprings from the parent chromosomes. And we also need to make sure that the entire population is moving toward some goal, right? And this is done by using some fitness function to eliminate some of the individuals in the population. And for the multi-arm bandit, and we can also view testing as multi-arm bandit problem, because in testing we have like we have a limited token, we have limited budget, like which could be viewed as tokens, whether it is time or whether it is like number of executions. We can always try to view them as tokens for us to play the gambling machine. And each decision we make could be viewed as like a gambling machine, right? We can choose which seed to use to generate test inputs. We can choose which mutation operator to use. And this seed or mutation operator could be viewed as a bandit machine or an arm of a bandit machine, because we don't know what is like the chance of getting a reward by choosing that that seed or that mutation operator, right? So for these decisions, we can try to apply the epsilon greedy algorithm. And the key is the value of this epsilon value. It shouldn't be too large, it shouldn't be too small. If it is too large, then we are doing like more doing more exploration, but we are not doing enough exploitation. And if we don't do enough exploitation, we are wasting our tokens on some non-optimal arms. And if the epsilon value is too small, then it means that we are not doing enough exploration. And if we don't do enough exploration, it means that we don't have enough knowledge to know which arm is optimal, right? So we are still like randomly trying different arms if we don't do enough exploration, if the epsilon value is too small. So this means that this epsilon greedy should be like using a small but not too small epsilon value. Normally 0.1 is a good choice. So that's all for today's lecture. And in tomorrow's lecture, we will have a recap of what we have learned in this term, and I will try to go through like the understanding level required for your final exam. So, okay, thank you for coming today. That's all. Thank you.